Sir. Uh, my name is Shiwan Yu from South Korea, Korea University. We are actually working on real-time support for hypervisor systems. And today we are going to talk about real-time issues and scheduling problems and how we can deal with it, which is performed by our lab members and Professor Chuck Yu. As we can see, the many advantages in current virtual machine architectures in network server systems. We can think about many interesting motivation examples from the embedded systems also. Because of the virtual machine architecture, we can accommodate multiple embedded systems over one hardware platform. You can run multiple operating systems. That means you can run multiple UI and you can run different applications for different operating systems. You can run, Apple's Apple Store products, or you can run Linux Mobile's Windows application without any porting and port of the applications. And because of the architectural support, you can enhance security and you can achieve trustworthiness. You can save your personally sensitive information in the cleanly separated, isolated execution environment. But in those existing systems, the virtualized environment, the real-time is a key challenging issue. Imagine that you can run, you have very smartphone which runs two operating systems, say Windows Mobile and Mobile or Google's Android. But sometimes it fails to taking the call. If sometimes your phone misses the call, then it is a kind of serious problem for the phone makers. And if you think about the DTV case, for $100 of DTV, the HD quality grades seriously without any reason. Even though you can run Safari or a web browser, it is almost useless. So, in those kind of systems, real-time is a key requirement, and we need to support real-time issues in those kind of embedded virtual machine systems. It does not mean that it requires not only CPU time, but also there is a time-bounded processing, so it is challenging. And we are trying to find some answers for this kind of question. Is real-time possible in the virtualized execution environment? And today I'm going to talk about the major obstacle in scheduling. We found some problem, and let me explain further in following slides. Conceptually, there are two problems in real-time scheduling in virtual machine. The first problem is that VM cannot accurately schedule tasks because the virtual machine runs over virtual time. That means even though you can know the actual physical time, but the virtual time passes arbitrarily, so you cannot schedule the guest operating system's task at very specific physical time. So real-time scheduling in virtual machine is quite different from auto-scheduling in physical machine. And secondly, hypervisor is not aware of the guest operating system's real-time task. So it cannot schedule any specific task at some physical time. Although hypervisor is aware of the physical time, it cannot schedule it because it schedules only the virtual machine or vCPUs. So how we can deal with it? Last Gen Summit, we proposed some architectural considerations and real-time issues, and we propose some solution about dealing with this kind of real-time scheduling problem. Because real-time scheduling has a long history. There are several related works in here, and compositional scheduling is one of the representative one. It aggregates the real-time workloads and creates aggregated periodic real-time tasks from multiple real-time sub-real-time tasks. Let's say there is a Xenon hypervisor, and MicroCOS 2 is runs as a guest operating system, and there are two real-time tasks. Say T1 has period of 50 and execution time is 7, and T2 has period time of 75 and execution time of 9 ticks. Then you can map those two real-time tasks and into one real-time periodic task. You can, by mapping, compositional scheduling framework enables you to map multiple real-time tasks into one abstract real-time task. The important thing in here is that the schedulable region is changed. That means if you change the execution period, the required CPU bandwidth changes also. In case of, let's say, if we specify the new task's period as 10, it requires only 28% of CPU time. But if you increase the period by 34 ticks, then it requires about 40% CPU time. So in here, you have to very carefully choose the execution period, and only in that case, you can safely schedule all the real-time tasks in virtual machine. And here's our contribution. Our first contribution is that we refine the scheduling theory itself. Because the compositional scheduling framework can specify the required CPU bandwidth. However, it cannot be directly applied to a real system because there is called quantization overhead. Every tick-based scheduling system has a notion of time tick. The scheduler quantizes its time, CPU bandwidth, to given unit of time and gives CPU time to the real-time processes. So because of this quantization effect, actually bandwidth has to be slightly more to the designated process, and we call that as a quantization overhead. From our analysis, we found that there is a complex relationship between the existing original compositional scheduling overhead and quantization overhead. As you can see the figure in the right-hand side, as you can change the interface period, in the small period area, quantization overhead is considerably large, although the compositional scheduling overhead is small. And if you increase the interface period, then the compositional scheduling overhead increases gradually, but the quantization overhead decreases. So there is a trade-off relationship between two overheads, and we need to find some optimal interface scheduling period. Because of this trade-off relationship, some kind of algorithm is required, and we have developed a specific algorithm to find the optimal interface. And our second contribution is that we are trying to incorporate the theory into actual VM scheduling. Because the